Welcome to Lecture 4.2. In this lecture, I'm going to cover all 5 of the EAS reactions that are typically covered in Organic Chemistry 2, and cover the mechanism of the important ones, and at the end of the video, I'll provide a table that has all the relevant information you'll need to understand the pieces of the 5 EAS reactions. The first one I want to cover is a very useful one, the Friedel-Crafts alkylation. Now, the name of this reaction helps us understand what it helps us do, what it allows us to do, and that's that it allows us to add alkyl groups, or different R groups, onto a benzene. This is really useful because that opens the door for a lot of different potential groups. This reaction uses an alkyl halide, right, an alkane with an sp3 carbon connected to a bromine, and essentially whatever's connected to that alkyl halide is able to be added onto benzene. We can see here we have a propyl or an isopropyl group of 3 carbons. Where the bromine is where the benzene will connect to it. So how does this reaction work? Well, remember the 3 steps. The first step is we need to activate the electrophile. So step 1. What happens is we use the FeBr3 catalyst, and luckily we're going to see this catalyst a few more times in this video. Right there are 5 different reactions, but this catalyst shows up for 3 of those reactions, which is very nice. How does it work? It's called a Lewis acid catalyst because the iron has basically an empty orbital that is able to accept electrons. Right? A Lewis acid is an electron acceptor. So how does FeBr3 work? Well, the alkyl halide, right? Remember that the double bond could potentially attack this in an SN2 fashion. We could imagine this on paper. It makes somewhat sense. But remember, benzene's way too stable. Alkyl halides are not that attractive. It's not good enough, not unstable enough to convince benzene to react. The bromine instead will attack and form a bond to iron. The product of this step is an intermediate where the bromine, which was neutral, has now traded its lone pair for a bond to iron. And that means that functionally it lost one of its electrons from that lone pair, giving it a positive partial charge. Or formal charge, I suppose. The iron would then gain a negative charge since it accepted one of those electrons in the bond. Now this is an unstable intermediate, and bromine really doesn't like being positive. And what can happen is that this bond will break the bond between the carbon and the bromine. That'll solve the bromine's problem. Right now we have FeBr4-. But interestingly, what we've done is we've created a carbocation. Now, carbocations, as we know, are extremely unstable. But that's the point. We need something extremely unstable for our benzene to attack. So the active electrophile, or the activated electrophile, for the Friedel-Crafts alkylation is the carbocation. So, great, that's the first step. Remember that this is the step that differs. The next steps 2 and 3 are going to be the same for every other reaction. So now we have benzene. It sees the carbocation that we formed in step 1, and it decides to attack. It's going to use one of its pi bonds, whichever one you use right now doesn't matter, and it's going to form a bond to that carbon. Drawing the product of this step. Oops, we can remove that. Let's say, and again, where we put this group doesn't matter for now. We have a group added there. There's our propyl, or isopropyl. And there's the hydrogen that was there, as well as a positive charge on the carbon that didn't get the activated electrophile. In the last step, we need a base to take that hydrogen and get us to our final product. FeBr4 is going to help with that, because it's going to decompose into FeBr3 and Br-. Now, a quick mention, a catalyst, it's very important, is reformed. It is not consumed in the reaction. If you needed 1 mole of FeBr3 to react with 1 mole of alkyl halide, we wouldn't call that a catalyst. We'd call it a reactant. In chemistry, the real catalytic nature of a catalyst is the fact that it is regenerated in the mechanism. It is required. We need it for this step, but we get it back at the end. So one of these molecules of catalyst can do endless cycles of the reaction. If you're really cheap, you can save it at the end and purify it and use it again another day. With that in mind, that Br- is going to be the base that we use. So the Br- will attack the hydrogen, bond electrons between the carbon and hydrogen will form a double bond. This is an elimination-like step. And that gets us to our final product. We now have added the 3 carbons we wanted to onto our benzene ring. And that's the mechanism of the Friedel-Crafts alkylation. Very similar to the Friedel-Crafts alkylation is the Friedel-Crafts acylation. Now, an acyl group is basically very similar to an alkyl group, except we have a carbonyl directly connected. People may be familiar with the acetyl group. That's where we have a methyl here. We call this specifically the acetyl group. But there can really be any R group here, and we can call this an acyl group or an acyl chain. So how can we add acyl groups to benzene? Well, using this reaction. Note that you can add any R group you want as long as you connect it. Instead of an alkyl halide, we're going to use a new functional group here, the acid halide. So not the alkyl halide, but the acid halide. It's like a carboxylic acid, except connected to that carbon is a bromine. We'll be seeing this again in the future. It's a very useful functional group. So like before, we can imagine that the benzene may want to attack here, but it won't really do that. It's way too stable. So first we have to activate the electrophile. We do this once again using FeBr3. So not only is it the same catalyst, it works in a very similar way. The reaction starts by bromine attacking the iron. Remembering that this is a Lewis acid catalyst, it gets attacked. This forms an unstable intermediate where the bromine has a very much unwanted positive charge. And what happens next is interesting. With the alkylation, we saw this bond break, forming a carbocation. Now that we have an acyl group here, this oxygen is actually able to help. We can avoid the formation of a carbocation. What happens instead is that this lone pair will form an oxygen triple bond, kicking out the bromine in the process. Once again, this leads to the formation of FeBr4-, and it also leads to the formation of a positive oxygen with a triple bond to this carbon. I'll go ahead and color code this in here, connected to the R group. This is now an sp hybridized carbon, and sometimes this is referred to as the acylium ion, the positive ion of the acyl group. Now, as much as oxygen doesn't like to have a positive charge, it's much better to put a positive charge on oxygen compared to carbon because of the fact that the oxygen does not break the octet rule in doing so. This is still nonetheless very reactive. It is the activated electrophile of this reaction. And now we'll use it in step 2 and 3 to finish the mechanism. So our benzene ring, again, wasn't willing to attack the original acid halide, but is absolutely willing to attack the acylium ion. We'll use its electrons and attack this carbon. Now, take a moment. It's quite a weird one. This oxygen is positive. So many students might think, well, wouldn't that benzene want to attack the thing that's positive? And while I understand the appeal of that, think about the mechanistic consequences. This oxygen is currently full. And while it is true that it has a lot of positive character, if we were to attack the oxygen, we would have to get rid of one of these bonds, because that oxygen is full right now. We could break it and give it to a carbon, but now we're making a carbon anion? That just doesn't seem to work. While we would make the oxygen neutral, we would not make a stable product. Instead, and something we're going to see a lot after the midterm, this double bond, this pi bond, will attack the carbon of the triple bond. That carbon is full, just like the oxygen was, except now we can break this double bond and give the oxygen its electrons. Following the product of this step, we have our benzene. Let me go ahead and color this carbon blue. There it is. Now it's a double bond to oxygen. You can see that the third bond, the second pi bond that is, broke. So now we have the double bond back. And that blue carbon is still connected to the R group, and there is the acyl group. We still have this hydrogen here, and we still have a positive charge. Just like before, since we have FeBr4-, we can use Br- to attack that hydrogen and eliminate to form our completed product. One key difference between the acylation and the alkylation is that we get to avoid a carbocation, and as we'll see later, that can be of great utility. For the third and fourth and fifth reaction, I'm going to cover the mechanism in a little bit less detail and focus much more on just forming the activated electrophile. In total, we have halogenation, nitration, and sulfonation. Unlike the previous two reactions, these are going to be adding very specific functional groups that don't have many options. Recall that with the alkylation and the acylation, we are able to add different R groups. We can add many different kinds of molecules, countless. But with these three, we're adding a very specific group. Starting with the halogenation, it's quite straightforward. We're going to use Br2, and it once again is going to react with FeBr3. That's the catalyst. The third and final time we'll be using the FeBr3 catalyst. By the way, I should mention at this point that if you're using chlorine, I've seen the AlCl3 catalyst used in place of FeBr3, accomplishing much of the exact same thing. So the Br2 will attack the iron. Again, we can imagine that the benzene might want to attack Br2, but it wouldn't be able to react with it. It's too stable. This is going to directly form our activated electrophile. Bromine is positive and iron is negative. At this point, this is the completed activated electrophile, and benzene is going to attack this bromine, kicking this out as the leaving group. Step 2 and 3 are the same as we saw above, and so I'll move on, but it's good to recognize where those activated electrophiles are and how they're made. The nitration adds a very interesting functional group called the nitro group. The nitro group, while shown as neutral, I'll elaborate a bit upon because it's a bit confusing. It's a nitrogen double bonded to an oxygen and single bonded to another one. This oxygen has a negative charge, and if you notice, that nitrogen has 4 bonds, so it's actually positive. Overall, the group is neutral, so you may see it drawn as neutral, but it is important to recognize that the nitro group does have these formal charges. Of course, this negative charge is stabilized by resonance with the other carbonyl. But now we know more about the nitro group. How can we add this to benzene? So we start by using HNO3 as the electrophile, and instead of using a Lewis acid catalyst, we're going to use an actual acid, sulfuric acid. How does this work? So HNO3 looks like this. Similar ideas before. We have an oxygen with a negative charge, it's resonance stabilized, and now we're going to put this in the presence of acid. Now, one thing that's very interesting with this reaction is we're actually going to notice that we had 3 oxygens in the starting material and only 2 on the product. Where did that third oxygen go? Well, in the presence of a strong acid like sulfuric acid, we can start protonating the structure. So this would be an OH, and just to be dramatic, we'll do this twice. I'll make this into water. Okay, so imagine this mechanism happened twice. What can happen next is that this oxygen, the one that's single bonded, can form a double bond and kick out this positive one, this water molecule, as a leaving group. That oxygen is now going to be lost, leaving us with this as the activated electrophile. Right? Here, when benzene wants to attack it, it will come in and attack the nitrogen, break this pi bond to give that oxygen its neutral charge back, and that leads directly to the nitro group being added. Don't forget, in the complete mechanism, you'll have to reform aromaticity, but in my opinion, this is clearly the hardest and most interesting step of the nitration. Last but not least, we have the sulfonation. Now, the sulfonation is a very straightforward mechanism. Once again, we're using sulfuric acid as our catalyst, and you'll see that SO3 has a Lewis structure that looks like so. You may note that this is an octet violation, but sulfur doesn't seem to care much about that. So what happens here, again, the benzene isn't able to react with this directly, but in the presence of strong acid, that sulfur, the oxygens of that compound, are going to be protonated, and this, funnily enough, is the actual activated intermediate. So one acid-base step, very straightforward. When the benzene decides to attack, it will attack the sulfur, once again breaking this oxygen double bond to give those electrons back to oxygen. Again, remember, that's the trick we're using to convince the benzene to react. Right? We're making that oxygen happy. The sulfo group looks something like this. Of course, we'd still have to deal with these things in the mechanism. I'll leave that to your imagination. It's the same as you saw above, so it's not much of an imagination thing. But I just wanted to show you what that functional group actually looks like, the sulfo group. And with that, that is all 5 EAS reactions. As I promised, here's a table. Feel free to take a screenshot or an image of this table and use it for your study. But this table contains all 5 reactions. I've grouped the first 3 and colored them red because they all have very similar mechanisms, and they involve the use of the FeBr3 or AlCl3 catalyst, depending on which halogen you use, as well as the activated electrophile and the base that's used in the mechanism. Now, one thing I want to mention is we have 5 different things now that we weren't able. So before, benzene was very stable. We weren't able to react with it. Now, we can add any R group we want, any alkyl group, any acyl group, many halogens, the nitro group and the sulfo group. We've opened the door to a lot of chemistry that involves benzenes. That's excellent. In the next video, we're going to look at what we can do after the EAS reactions to further modify those groups.